Yeah, good afternoon everybody. Welcome to this course on space-time codes and MIMO. This course will be covered in two parts. This is the first part. So the first, that will be three lectures. So the outline of this course is basically I will be introducing concepts of what are the problems that occur in a wireless fading channel. Then among the many solutions, I will show that MIMO is a solution. Then for the MIMO channel, we'll do some modeling so that we understand how a MIMO channel works. And then we go on to see what are the design criteria for the MIMO channel. That's the first part. In tomorrow's lecture, I will basically take care of what is the main advantage of MIMO. And then in the third lecture, we'll basically address space-time codes. Okay? Okay. Right. So, it's a very important topic, space-time codes and MIMO. It is there in all the current standards. It will be there in all the future standards. So, MIMO is definitely going to be the future. So, anybody who wants to have work in wireless communication has to go through both, have a good understanding of MIMO and space-time codes. So the first topic of today's lecture, what are the impairments that happen in a MIMO channel or in a wireless channel? First, as in case of the wired channel, that is referred as AWGN, the wide Gaussian noise channel, it is the thermal noise, it is additive noise, it is there because of the receiver. The second and important thing you see in the diagram below is as you go further away from the transmitter, what you see is basically the ratio of the received signal to the transmit signal decreases as you move further away from the transmitter. You see the curve, and this curve goes down at least as square of the distance. Okay, so it is inversely proportional to the square of the distance. So this is a significant loss, but it is uniform and it goes down in a proper format. You see, it is a 1 by d square curve. The second problem is a bit more important. You see that it is called shadowing. This is because, as you see in the diagram again, there is some obstacle, some building, something has come in between the transmitter and receiver. That's why, and this phenomenon will vary because you are moving, so at some times you will have a very large decrease in the amplitude and then it may increase as obstructions come and go. So this is a slow process in the variation of the received signal power. You see the red curve basically shows the effect of fading. So suppose you are crossing a building. So as long as you cross the don't cross the building, there will be a huge dip in the power. So this is what is called as shadowing. The third issue is basically what you see contributes to the fading. It combines multiple effects due to the movement of both mobiles and the reflectors. Essentially, when a signal is being transmitted, it is not just going one direction, it is going multiple directions and it is getting collected at the receiver. Okay? So because of this multipath causes a lot of problems. It causes variation in the amplitude in a very fast manner. So you see the green curve that basically is capturing the effects of fading. Okay. So these are the four major impairments in a wireless channel. Now fading can be due to many reasons. It can be due to attenuation, it can be due to distortion. So distortion is distortion, the rounding of the curves. So that's one form of distortion. There are many other possible distortions. So when you transmit in open air, there are many different sources of distortion that come into picture. Then there are delays because different paths travel different distances, they have different delays. And they also have phase shifts. So in effect, because of the fading, you see that the first lower curve is basically the signal to noise ratio versus probability of error for the AWGN channel. The curve that is going fast below, you see that curve that is going to 10 power minus 6 at around 10 dB, that is the AWGN curve. The other curve you see that is going down linearly is what is the effect of fading. This is a Rayleigh fading channel, and you see that even at 25 dB you are just around 10 power minus 3 probability of error. It's a huge loss. Okay. Typical systems today work at a frame error rate of 10 power minus 1.1 packet loss. That would correspond to a bit error rate of roughly 10 power minus 6. So you see that if you extrapolate this curve, the curve that is going linearly down, this would go to around 10 power minus 6 at around 50 dB. So what you require is 40 dB more power to get a performance that is acceptable on a wired line. That is a huge amount of power, 40 dB. So if you divide 3 dB amounts to basically doubling of the power. Now this is 40 dB. So you are not divide by 3, what do you get? So this 2 power 12 point something times increase in power is required to get the same performance as a wired channel. This is a huge effect. So in essence, the major impairment of a fading channel or the wireless channel is fade. Recollect from the previous slide, and fade is due to, or it is the small term effect, the small variations in the received signal amplitude due to multi-path, that because each signal is traveling multiple paths. Okay. Now we will come to classifications of fading. Because of the very random nature of these variations in the received power, we need to classify them because different techniques will be required to combat different types of fading. So first is multi-path spread. So you see the figure below, there are 4 buildings, 1 transmitter. You see the received signal at the car is coming from at least 3 different directions in this figure. One is coming straight with a delay of 0. The second one is coming with a delay of 8 microseconds from the second. So a measure of the delay is what is called as a delay spread. It gives you the time duration over which you can expect signals to be received. Okay. Now the signal amplitude can go down significantly. So there is some criteria that you will put that the signal is 100 times below the first signal or something of that kind. And then you measure the root mean square delay. That gives you the effective spread of the channel. That's the first parameter, that is multi-path spread. The second parameter is basically what is called as the coherence bandwidth. What you see below here, this is an actual channel measurement from a German city called Darmstadt. What you see is, it is a function of both time and delay. Okay, you see that? So your received signal can be modeled as a filter whose coefficients depend both on time and delay, ht tau, so the green one. So the output yt is basically going to be the convolution of the input xt with the channel ht plus tau. To that you add the Gaussian white noise nt, and that is what is the complete received signal. So you see that it's just nt. It's not very clear because the resolution is not good, but this is what is the entire signal. Okay, so by characterizing the multipath spread, we have been able to get immediately the model of the received signal and the model of the channel in terms of time and the delay spread. Okay, so second parameter is coherence bandwidth. So what you see below in the figure is basically the Fourier transform of the filter, which is now a function of time and frequency. Now you see, as frequency changes, the response of the filter changes. It is important. This is because if you have transmit two signals at two different places, it gives you two different fields. Okay, two different responses from the, so as signal transmitted at this frequency and a signal transmitted at this frequency or this frequency sees an entirely different power, entirely different power. Okay, so this is an important parameter that tells you how far you need to be for to actually undergo different fades. I will make it a little bit more clear in the later slides. The third parameter is coherence times. So you see it basically tells you how far apart the signal should be so that it varies in time. Okay, so these are the three parameters that are of importance in a fading channel. People do also put Doppler spread, but Doppler spread basically is taken care by the coherence time. It causes variation in the channel as a respect of time, so coherence time is sufficient to characterize that. Now based on these three parameters, we have a classification of the fading channel. So the first channel is when the bandwidth of the signal is significantly less than the coherent bandwidth. So in this case, what you will see is the frequency response that I showed you, HTF, that will be flat. It will, so the signal will just see a single it will just see a single value. Okay, any amount of variation will not lead to change in frequency, will not lead to change in the received power. So that's why it is called a frequency flat channel. All parts of the signal receive the same attenuation. In contrast, if bandwidth is greater than or equal to or comparable to the coherent bandwidth, then what happens is different parts of or different frequency components of the signal will undergo different fades. So this leads to a very different sort of distortion that has to be taken care of, and OFDM is one technique that takes care of that. Okay, I hope you are following me. Okay, so proceeding further, so this one set of classification based on coherent bandwidth, that is frequency flat. So in frequency flat channel, the received signal, all frequency components of the transmitted signal receive the same attenuation, so it is modeled as a single tap. If the bandwidth is greater than or comparable to the coherent bandwidth, then different parts of the signal receive different attenuations, and due to that, what you have is a multi-tap channel, that is frequency selective. Second classification is because of the coherence time. You see, if the symbol duration is significantly less than the coherence time, then the signal attenuation will not change. So when the symbol duration is significantly less than the coherence time, okay, so the signal will not change. In contrast, if the symbol duration is large, okay, that's where what you will see is multiple different symbols will go through different attenuations. Okay, so each signal will see a different fade. So that's why you have the classification of fast fading and slow fading. Okay, so these are the two classifications, frequency flat and frequency selective. Frequency flat, all parts of the signal see the same attenuation. Frequency selective, different signal components or frequency components see different fade. Fast fading, the channel is fading fast. So this is because the symbol duration is of comparable time with the coherence time. Okay, if the symbol duration is large, okay, or if the symbol duration is small, then the channel will see repeated durations will see the same fade. So it is slow fading. Okay, so these are the two classifications. I hope that is clear. It's just recollection of your wireless communication basics. Now, as we have seen in the second slide, major problem is fading. We want to address fading. One simple straightforward technique is put more power, transmit more power. But it's not a good technique because As I have already told you, you need to spend 40 dB, 2 per 12 times more power to get the same performance. That is not feasible. It's too much. Okay. Is there something else? And the good point is, yes, there is something that we can do. And that is what we are doing at. See the channel that we have seen, or some examples we have seen, there is a possibility that the channel has some correlation in time, frequency, and also in space. So space is multiple antennas. So if we are able to extract this correlation, then we will definitely be able to perform better, and that is what is the diversity concept. Okay. You can think of it like this. You are doing investment banking, so you want to invest in some ventures. They are very risky. You are not sure which one will give good returns. So what you do is you break up your investment into small parts and put it into multiple investments, so that you get the benefits at least somewhere, right? The same idea is there. You take a signal, if you transmit on one channel, there is a possibility that channel may go back, but if you transmit on n different channels, n different independent channels, the possibility that all of them go back is going to be very poor. Okay, that probability is going to be very small. So this is the concept of diversity. So you are essentially basically exploiting the variation in time, frequency, or space of the received signal amplitude to exploit, to get multiple copies of the same signal, and you hope all of them do not fade together. Okay. The important point here is, if there are two inputs, they should be uncorrelated. If they are correlated, then if one signal is faded, the other will also be faded. So the important point here is these inputs have to be uncorrelated. Okay. So see that, suppose P is the probability that your amplitude is smaller than a certain amount that you require at the receiver for demodulation. Okay. Say epsilon. Your received signal should be greater than epsilon for proper detection, because it's a random variable, it's a random process. It may be the received signal may be less than that. Let P be the probability of that happening. Now if you have n independent parts, what is the probability that all of these n parts will fade simultaneously? Yes? Yes, that probability is going to be P power n. So what you see is, if the, for an example, take P is equal to 0.1. Okay, this P is equal to 0.1, 2. Okay, n is equal to 2. So now, what is the probability of both of them fading together? It is P square, that is equal to 0.01. So you see the probability that both of them fade together, that is you get a bad signal, is going to be significantly smaller. If you make it 3, n is equal to 3, it is going to be 0.001. It is 1 in 1000. So it has decreased. The probability of getting a bad channel among 3 channels has further decreased. So you see, the simple concept of adding multiple replicas on independent channels has significantly reduced the probability of fade. Let us see what this effect will have on the probability of error curve that we saw. But before that, there is a classification. There are many different types of diversities, as you see, because there can be a correlation in space. We have the diversity. There can be correlation in frequency. We have frequency diversity. We have time diversity. There can be multiple replicas because signals are coming later on. This is called multi-part diversity. So there are 4 different classifications broadly of diversity techniques. What in this lecture we will basically focus on MIMO, which is a part of space-time diversity. Okay. This slide basically shows you the variation with number of antennas. The red signal is basically with the received power for a single receive antenna and a single transmit antenna. You see the red signal? You see Sometimes it is near 0, but you see around 50 microseconds, my pointer is showing that the signal is more than minus 20 dB below. So that is on more than 100 times power has decreased in the, and the time scale is nanoseconds. Okay. So in less than 100 nanoseconds, you see the signal power has dropped by 100, then again it has come back to 0, then it's going down. So you see it's large variation in the received power. Okay. So the mean power is roughly around 0 dB. It's just 2 or 3 dB, minus 3 dB. But you see the variance is large. Okay. Almost you see it is a variation of minus 35 dB in the received power. So 30 dB would correspond to a decrease by 1000 in the received signal amplitude. So for a single antenna, you see the variation in 800 nanoseconds, the signal is varying from 0 dB to that is from 1 to 1000 times. The huge variation. Now see the blue curve, that is for 4 receive antennas. First thing you observe, the mean is more than 10 dB. So this is because the signals are contributing together. So you are getting a 10 dB. You see the mean for single antenna and the mean for 4 antennas is a gain of 15 dB. You see? So you have an average receive power that has increased by 15 dB or 13 dB. Second part, you see the variation in signal. The signal is never less than 5 dB. So you see the variation is now 10 dB, but it is never less than 5 dB. Here, total variation is around 10 dB from 5 dB to 15 dB, but the signal is never less than 5 dB. You see, here it was 1000 times smaller, but here it is always greater than 1. 5 dB would correspond to roughly, I would say, 3 times. 3 to 4 times what you had got at a single antenna. So you see there is a significant improvement in the received power, and that is the concept of diversity. So 2 points of importance here. The mean tells you the average power that you are going to get. That basically gives you what is called as the array or the coding end, and the variance basically gives you how much the signal is varying. The less the signal is varying, the better. So it has higher diversity. More the signal is varying, it has poor diversity. So variance is of the received power is an important parameter in classifying a fading channel. Okay. So I hope this example makes our previous classification and discussions much more clear. So at this point I would expect you to take a quiz that would be taken at the end of the class. I'll move on to the next slide. We'll see the MIMO channel. So now the single antenna, that is single input, single output fading channel, is characterized by this figure here. You have a transmitter, the signal Xi is transmitted, the channel gives a fading coefficient, that is H, and Yi is the received signal. So the output received signal here is Yi is Xi plus eta. This channel is flat, that means all components of the signal receive the same attenuation H. So that's why there is only one tap. Second, it is slow fading, so that is the entire symbol will always see one fade. Okay, so this is the input-output relation for the seesaw flat slow fading channel, or it's also called as a static channel. Another variation is what is called as a quasi-static. So the channel H is constant for multiple durations, multiple received signal duration, so multiple I's, and then it varies after a certain block length. We'll come to that later. So H is typically modeled as a complex Gaussian. So the amplitude of H is Rayleigh, and then this eta is the additive Gaussian noise with variance 2 sigma square, and we assume H is known as the transmitter, because if you don't know H, no matter what you transmit, you cannot decode. H has to be known. Okay. Differential modulation basically allows you to get a rough estimate of the channel. So some estimate of the channel is definitely required. So this is the CISO model. Now next we go on to the MIMO model. So you see here there are two single antenna fading channels, two CISO channels. They are parameterized by the channel coefficients H1 and H2. I can write it in a matrix form. So Y is basically the received vector consists of Y1, Y2. The two received symbols. X consists of the two transmitted signals X1, X2, and H is a diagonal matrix with the two coefficients H1 and H2. Now coming to the generalized model, when you transmit from X1 from antenna 1, this is going to be received at both receiver 1 and receiver 2. This is modeled by H11 and H12. Okay? H11 and H21. H1, so you are transmitting from X1 and receiving at 1. H21 you are transmitting from antenna 1 receiving at antenna 2. So you see this H21 is the channel coefficient from antenna 1 to receiver 2. Similarly H12 is from transmit antenna 2 to receive antenna 1. H22 is from the channel coefficient from the second transmit antenna to the second receive antenna. Okay, so this is a flat slow fading MIMO channel modeled by Y is equal to Hx plus theta. We will go a little further into the general model of MIMO. So there you have NT transmit antennas, NR receive antennas. Here if there is variation in space, okay, if the channel varies in space, then MIMO is going to exploit that. If there is no variation in space, okay, the channel from antenna 1 to receiver antenna 1 is same as channel from 1 to receive antenna 2, you will only get coding gain. There will be no diversity because the two channels are same. But if there is diversity, that is the channels are uncorrelated, then MIMO will exploit that. We will see that later on. And another advantage of MIMO is it also takes care of multipath spread. The reason is if you have multiple signals coming from multiple directions, they will combine differently at different antennas. Okay, so this different combination will give to diversity, and that is exploited by MIMO. So the ability to turn multipath propagation into a benefit for a user is what is a key feature of MIMO. Some definitions and notations. As I have told you, NT is the number of transmit antennas, NR number of receive antennas. Let XJT be the signal transmitted from the J8 antenna. YIT is the receive signal at the ith receive antenna. Then using our filter model for a CISO channel, remember that what you transmit from antenna J is received at antenna I. The channel is a function of both the delay and time, and because that the signal is being transmitted from NT antennas, we are adding the convolution output from all the antennas at the receiver. Okay. So this part is basically the convolution of the what you transmit from jth antenna and receive at the ith antenna and the channel coefficient, general channel coefficient. In the general case, from the jth transmit antenna to the ith receive antenna. The small circle basically represents convolution. Okay, there are NR such YITs. Putting them together, so we can write in matrix notation, YT is basically a vector of the NR received antennas or signals received at the antennas at time t. Similarly, define xt as a vector of signals transmitted from the NT transmit antennas. Eta 1 to eta NR are the noise that is added at each of the NR receive antennas. So combining this previous equation, collecting all the YIs together, we can write in matrix notation YT is HT tau, where HT tau is a matrix now Convolution here means each element here convolves with each element here and then adds. Okay, and eta t is the noise that is added here. So what this means is x1t convolution with h11t plus h12t h12 convolved with x2t, so on and so forth. Okay, so this is a more compact representation of the received signal. Okay, yt now is a vector, ht tau is a matrix. It is called as the channel response matrix or the MIMO channel matrix. Okay, now there are some special cases. Suppose you have one receive antenna, anti-transmit antenna. So this is called as the MISO case, multiple input, single output. That's why the abbreviation is MISO. So in this case, your channel matrix becomes a row vector. Okay, it's one receive antenna, so just one output. The second special case, your channel matrix is an NR crossband vector. Okay, so there is only one transmit antenna, multiple receive antenna. So what you received at the first receiver is basically convolution of the channel with x1t. Similarly, what you received at the second antenna is y2t, that is a convolution of h21, the channel coefficient from the first one transmitter to the second receiver convolved with what was transmitted, xt. So this is the second special case of SIMO. Both of them are there in practice. More with respect to dynamics. For example, it is more feasible to put multiple antennas at the transmitter rather than the receiver, because putting multiple antennas at the receiver makes the device costly. Okay, so that's now when in such a case there are multiple antennas at that base station. Okay, and only one antenna at the receiver. So the downlink, the channel from the base station to the receiver is a MISO channel, and the uplink, from the user to the base station, that is a SIMO channel. That is, he has only one antenna, but there are multiple antennas at the receiver. So these are very practical cases actually. Now, there is one important assumption that has been made to simplify the channel. You see here the channel, the generalized MIMO channel model that we developed is a convolution of NT-NR channel coefficient what the NT transmitted signals. Yeah, see here, this channel has NT-NR coefficient. These are convolved with the NT transmit coefficients. So totally there are how many convolutions? Yes, they are going to be NT-NR convolutions. Okay, a lot of work. It's very I would say very most general channel that could be encountered. Practical cases, the channel is much simpler. This is because of the narrowband assumption. That is, the signal transmitted is very small. Okay, and two paths that are from the transmitter to the receiver, they are identical except for a phase shift. The delays are not so large that they cause a multiple time. And so they are arriving from different angles based on the geometry of the antenna and based on the reflectors and the okay, but they have a similar phase shift. So see that signal received at the second antenna is just a phase shift of the first transmit antenna. So based on this narrow band assumption, okay, so the signal bandwidth is small, so the time duration is large. So because of the large duration, most of the signals will from the multiple paths will arrive at a very short part, within a very short part of the symbol duration. So the receiver is not able to see that they are different replicas. He only sees the same signal coming with a different phase. This is how it is. Okay. So assuming there are k different scatterers, okay, using the narrowband model, what will happen is, here you see that your ykt will be equal to y1t e power minus j 2 pi sine theta, which is a function of the angle with the transmitter. Okay, d is the separation basically between the antennas and the wavelength. Okay, so essentially what becomes is the multiple signals from multiple reflectors combine in the same time duration with different phase. Okay, such a channel we can assume is not time varying in nature, and for this, if it's not time varying, it is going to be constant. Then we get the original model that we got from the seesaw flat fading model. You see y is hx plus eta. The variation in tau is not there because of the narrow band assumption, and the variation in t is not there because we are assuming that the channel is not varying with time, it is constant in time, or at least it is constant in the duration of interest. Okay. These are some notations basically, you just need to understand the concept behind it. I hope you are following that. So, what is this channel model? This is a MIMO channel model. Is it frequency flat or frequency selective? It is a flat fading channel because the coefficients are not varying. Okay, delay spread tau is very small. Okay, so each channel basically is actually not a function of tau, so the variation in frequency does not occur. Okay, so it is frequency flat, and because it's not, we are assuming it is not time varying, so it is basically slow fading channel. It is, the symbols is a single fade for a given channel. So now this part is what is called the basic starting point for all MIMO derivations. Okay, but it is not sufficient to completely characterize the fading channel. This is because the coefficients have a random nature, and there has to be some mathematical model to model this random nature, and that comes from probability and random processes. Okay. So here, in addition to this h, what we see is the coefficients hij, they are varying as complex Gaussian random variables with a 0 mean and variance 1. Okay. So this assumption that the entries of the NT cross NR MIMO channel are complex Gaussian is very important, because this captures the randomness of the channel H in the narrowband model due to multiple scatterers. Okay, just two scatterers, this model would not be efficient. This model is efficient when the number of scatters or the K that we assumed in the previous case is more large. It's a rich scattering or environment, so signals are coming from multiple scatterers with very little delay, so the receiver sees just a phase shift. But these combine differently because of the different combinations. Okay, remember the law of large numbers. Okay, if we have multiple random variables added together, the large number of random variables added together, then the overall effect is you see a Gaussian random variable. So that's how this model works. Okay, so H is a complex Gaussian random matrix whose entries are complex Gaussian. This is because we have assumed it is a narrow band and there are large number of scatterers in the environment. Okay, it's a very practical model and it gives us the worst case performance. Okay, so X, as we have told, is a transmit symbol, and for the remaining part we'll assume it is from M-cam or Q-cam, whatever you take, and the noise is a vector with each entry being complex Gaussian with variance 2 sigma square. So this is the basic MIMO channel model that we will be assuming for the rest of the course and for the second module of the course. Remember this, Y is a received signal vector. Okay, it is a 1 cross NR vector. H is a NT cross NR channel. It has NT cross NR entries. Each of them is complex Gaussian. X is a NT cross 1 transmit signal vector, and eta is the noise added at the NR receivers. Okay. This channel, as I have told you, is a MIMO, slow fading, flat channel. Okay. Remember that. Now from here we go to a very different sort of channel. That's what is called as the erasure channel. The erasure channel is actually an extreme case of fading. Okay. So that is either you receive the signal or you basically the amplitude is so bad, the received signal power is so bad that you basically don't see any signal at all. So it's an extreme case. It happens. It also models the case wherein at the application layer, if you remember, if there is a packet loss, you can just say that this entire signal has been erased. So this also models that case. A very important channel used especially in the case of LDPC. So I thought that linking our fading channel model to erasure channel model will help in two ways. Your understanding will give a basis for working towards LDPC and turbo codes in one direction. Second, it will simplify some of the concepts of the fading channel. So remember from information theory, this is how a binary erasure channel is modeled as. You transmit a 0 and with a probability 1 minus epsilon you receive a 0. But there is a non-zero epsilon probability that this symbol is totally erased and it is represented by some symbol that is neither 0 nor 1. You can take it as X or Y, capital Y, whatever you say, or a capital E that represents an erasure. So there is no symbol received. The power is so bad that the receiver doesn't decide whether it is 0 or 1. Similarly, when you transmit 1 with the probability 1 minus epsilon, you received a 1. Otherwise, you just say that I don't know what it is. Okay? This is what is called as an erasure channel. A code over an erasure channel has certain parameters. Again, from information theory, N is the length of the code word, K is the number of information symbols, and D mean is the distance between two code words, or the minimum distance between all two distinct code words. So this I am taking from information theory. Now, one important concept that I am introducing in this slide, that is what is called as an ergodic erasure channel. Remember that we have got two classifications of the channel till now. One is flat and one is frequency selective, other is slow and fast fading. Now there is a third concept coming in, that is ergodic. We'll say a channel is ergodic if it is memoryless in the case of an erasure. What does it mean? If you transmit a symbol or a code Ci at a duration I, it does not affect next symbol. So if C1, Y1 depends on what you transmit at C1, Y2 will depend on C2. It will not depend on Y1. So this is a memoryless channel. Okay? So if C1 is erased, there is no guarantee that C2 will be erased. Okay? The erasures from each channel is each symbol is going to be different. That is the concept of ergodic. Okay? Remember from random variables and processes, an ergodic process is where the time average is equal to ensemble average. Okay? So basically each instantiation of random variable yi results in a random variable. So the variation from each symbol is going to be entirely different. Okay? And remember and recollect, it's an erasure channel. There is no errors. There are only going to be erasures. There are going to be no errors. Thus, in contrast to ergodic channel, we will naturally have a non-ergodic channel. See that? I am underlining. So, what do you expect? So, if a ergodic channel does not have, the ergodic channel has no memory, a non-ergodic channel will have memory. Okay? So, to take that concept into mind, what we have done is we have divided the code word into blocks. Each block of, remember the code word is of size n, we are divided into L blocks, so n by L total blocks. So each block has n by L bits. Okay, see that. The code word is now divided into sub blocks. Each block erased independently. So what will happen is, if there is an erasure in C1, first bit, so there will be an erasure in all the bits, that NL bits of the first block. Okay. So this is a block erasure channel. Remember, this block erasure channel has memory. Why does it have memory? Because if the first symbol is erased, entire block is erased. Similarly, if the first symbol or any symbol of any block is erased, it means entire block is erased. It's a block erasure channel. It's an important concept. So see that this channel has memory, and therefore because it has memory, it is natural to combine the received signal into blocks. So you have the received vector y consisting of blocks, L blocks, and then your channel is characterized by the transition probabilities, that you transmit C and you receive Y, you transmit the code word C, receive Y, so it is divided into the L independent blocks. So you see it is the probability that each block erases or not. Okay. So now you see the non-ergodic channel, it was a product of the non-ergodic channel. Each channel, each received symbol, it depends on the transmitted symbol, varies independently. So it is a product of capital N terms, capital N probability terms. Go to the non-ergodic terms, there are only N blocks, each block is varying independently, but within the block, the bit, if one bit is erased, entire block is erased. So here there are only capital L probability terms. Okay. So I hope you now have got the concept of ergodic and non-ergodic. Most channels in natural scenarios will be non-ergodic. This is because when you transmit a symbol, okay, of a given duration, for even example you take GSM, the symbol duration would be of order of milliseconds. Okay, but the channel, typical channel in an indoor environment or in a slow environment will vary with a very, the duration that is a function of seconds. So the entire packet of 1000 bits can go through while seeing the same channel. Okay, so you will see this block model coming into picture. So most of the practical channels where the mobility is small, there are large number of scatterers, is going to be non-ergodic. So this concept of non-ergodic erasure channel applies to fading channels also. So it's a very nice way of introducing it. So please remember that an ergodic channel and a non-ergodic channel. Okay. Any questions here? So we have now three classifications till now. First classification, fade flat, frequency selective. Second classification, slow and fast fading. Third classification, ergodic and non-ergodic. There is a new concept entirely that is being introduced now, that is the concept of degrees of freedom. It's a very old term. It was introduced in statistics way back in the 18th century. It tells you number of values that are free to vary. Okay, so you receive certain inputs. The number of values that are free to vary is basically what gives you the degrees of freedom. For example, if you have a random vector, okay, remember from your linear algebra class, etc., you have a vector, okay, or from your linear system solution, you have sometimes you have one solution, sometimes you have no solution, sometimes you have multiple solutions. The multiple solutions are parameterized by free variables. Remember that you have done even in 10th class. Solution of system of linear equations. So suppose it is parameterized by one variable. That means there is a 1 degree of freedom. If it is parameterized by two values, then there are 2 degrees of freedom. Okay, so in random vectors also the degrees of freedom basically tells you the number of components that you need to fix to know the complete vector, complete random vector. Okay, now why is this going to be useful for us? Recall that what you receive. Okay, the probability of receiving Y given your transmitted code word C, it depends in an ergodic channel on capital N number of terms. So the ergodic erasure channel has n degrees of freedom. You need to fix all n of them so as to know the complete code received signal. Similarly, for the non-ergodic case, tell me guess what would be the number of degrees of freedom? The L terms. Capital L, the number of blocks. If you know the capital L transition probabilities, you will know the complete transition probability of a code word. So the number of degrees of freedom in a non-ergodic channel is going to be L. Okay. Now, as a simple case, example case, you see that N in a packet would be of at least 1000 bits. That is typical, but L may be of order of 3. So you see the degrees of freedom vary a lot when you assume an ergodic channel and a non-ergodic channel. Now we'll link these degrees of freedom to another concept that I had introduced before. Okay, that is diversity. Now look at this. What you have is a repetition code. What is the repetition code? Suppose you want to transmit a 1. You repeat it capital N number of times. Okay. So I want to transmit 1. So suppose capital N is equal to 3. So what I will do is I will transmit a 1 3 times. Okay. So this is what I will transmit. So now this repetition code has the following parameters. N is the number of time it is received. 1 is the number of information bits. So here in this case it is going to be 1. There are only 2 possible code words. It is all ones or all zeros. Okay. So C1 is the first code word and C2 is second code word. Okay, these are 2 possible code words. The Hamming distance between these 2 code words is the number of places it varies, and you can easily see that they are varying in 3 places. So the code word is going to, so the the minimum distance is going to be 3. And for a general n repetition code, the minimum distance is going to be n. Okay. Now, suppose I have transmitted a 0 using this repetition code and I have received something. What is the probability that there is an error? Yes, just think about it a bit. I have already given an answer. Probability of error will be epsilon power n, where epsilon is the erasure probability. Why would that be? It is simple. Suppose among the n bits that were transmitted, take the example of 3. You have 3 bits that were transmitted. Suppose this bit is erased. So what you received, I am writing here, what you received Y is going, suppose is going to be erasure E11. So what would you decide? Obviously it would be 1. Now suppose this is also an erasure, second bit is also an erasure. What would you decide? Again it is going to be 1. Why is that? Because even a single 1 only means that a 1 has been transmitted, because a 0 cannot be received as 1. As simple as that. Okay. So the only case when an error is possible is when all three are in error, erasure. All three bits are erased. So now you don't know whether it is a 0 that was transmitted or a 1 that was transmitted, right? So this is the case where you are not able to decide at all. So with this simple repetition code 3 times, you see an error occurs only when all three bits of the code are erased. Okay. So that's why once you generalize this for n equal to n number, you see the probability of error is given by epsilon power n. Okay. So now your n, you see, remember that first we started n is the length of the code word. Second, what did we say? N is the number of degrees of freedom for a ergodic erasure channel. It is the number of transition probabilities that you need to know to get the full information at the received vector y. Okay. Now third thing, the probability of error is also now linked to n. Can we generalize it a bit more? Suppose I take a code word, it is not a repetition code, it takes k information bit, codes to n, codes it to an n length code, and the distance between any two code words is at least d min. Okay? Now such a code will fail to decode an erasure pattern if and only if the pattern contains the support of a non-zero code word. Now what is a non-zero? What is the support of a non-zero code word? It is basically the set of non-zero values of the code word. Okay, I don't know whether you are able to see that or not. It is right at the end. I think in my screen it is cut. The support vector. The support of a code word is a set of non-zero coordinates. Okay. Let me explain the concept of support vector. So you take an example. C1 is a code word. Okay. Suppose 1 0 0 1 0 1. Now the support vector of this code word is basically the index, okay, of no, this is 1, this is 4, and this is 6. So the support vector of a code word is the number of non-zero, is the index of the non-zero elements of the code. Now what is being said is two code words will be in error if their support, if one support vector is a subset of another support vector. I'll give you an example. Take another code word C2. Okay. Now C2, this is another code word. The support vector here is 1, 6. Okay. Now you see that this support vector is a subset of the previous code word. So what will happen? Suppose this bit is in an error. So what you have received, the fourth bit is basically erased. Okay. So you have an erasure in the fourth bit. Now among the two code words, which one can you decide? So in such a case, you cannot decode. So that's what is being made, that's the statement that is being made. An ML decoder fails to decode an erasure pattern if this pattern contains the support of a non-zero code word. Okay. As an assignment, I have asked you to do that. please develop on the logic that I have given in this example. Okay, from the example it is very clear. If there are two code words where the support vector of one of them is a subset of another, then there are going to be patterns that will cause errors. All patterns may not cause errors, but there will be certain patterns that will cause errors. Okay? Now, let psi ml be the number of such erasure patterns with weight W. Then probability of error can be shown to be equal to this value. Okay? It's a very old and very famous result that you can see in any of the books on erasure channels. It's widely used in LDPC decoding because assuming an erasure and decoding is much simpler than it's a polynomial time decoding in turbo codes and LDPC codes, while assuming it to be in error is exponential. So that because of that, this erasure channel has gained significant importance. Okay. Now this is going to be called error. You see that for the summation is from the minimum distance to number n. Epsilon is the probability that there will be W errors. 1 minus epsilon is the probability that there are no errors. There are totally psi ml patterns with this weight. So this is the total contribution of weight W. Summing it over all W gives us the probability of error for this code word. Now, as epsilon becomes small, you see this term tends to 1, the second term. This term tends to 1 as epsilon tends to 0. Okay. So what will be left is epsilon omega term this. So what you can write is for small epsilon, probability of wrong decoding D on an erasure channel is a function of D mean. Okay. The minimum distance of a code is now related to the power of the minimum distance is now related to the probability of error as a power term. Okay. Epsilon power D mean. Okay. So while the channel, remember that, while the channel has n degrees of freedom, it is now reduced to D mean. Okay. So this is a second concept in degrees of freedom. Remember that. You have a separate degrees of freedom of a channel that is equal to the number of values you need to know. So from a given input to get the output completely, right? For the ergodic erasure channel it was n terms. For a non-ergodic channel it was L terms. Now if you have a code, then the degrees of freedom of a code now has reduced. The probability of error now depends on the minimum distance D. Okay. So this is another concept. Degrees of freedom in a code and a degrees of freedom of the channel. The degrees of freedom of the code is upper bounded by degrees of freedom in the channel. The reason I want you to understand this concept is what will come in the next slide, on the next few slides. Okay. But till now just remember that degree of freedom has a direct role to play with the probability of error. The higher the degree of freedom, the lower the probability of error, because it will result in a high, as I told you, if epsilon is 0.1, if d min is 2, it is going to be 0.01. If d min is equal to 3, it is going to be 1 by 1000, 0.001. So this min is playing a very important role in the probability of error. Now come to the case of non-ergodic channel. Okay, and in a block we are going to repeat it. So we are using a repetition channel, repetition code with the same number of repetition as the block length of the non-ergodic channel. So L is a common parameter. It is equal to the number of repetition and it is also the number of blocks in the non-ergodic DEC. It is very simple from the previous argument that I have given that the probability of error here is epsilon power L. Okay. So now again we confirm that degrees of freedom again is bothering you. It is giving you, it is very important from a probability of error perspective. Okay. It tells us how far the probability of error is going down. Now, similarly, what happens when you take a non-trivial code? I won't go through this derivation, but you can understand from the previous case what we have done. The probability of error is again going to be proportional to, dependent on L. Okay? Provided L is going to be less than the minimum Hamming distance of the code, and that is typical. Remember the example I gave you, N was 1000, L was equal to 3 and more in codes that are being used today, Hamming distance is definitely going to be greater than 3. Recollect that Huffman code has a dmin of 3. Right? From your information theory and coding, recollect that the Huffman code has a dmin of 3. Okay. So, even if you don't understand that, still please understand that the degrees of freedom, the Hamming distance is an important parameter for an erasure channel probability of error perspective, because it gives us the power term, the number of epsilons that are going to be multiplied to get the probability of error. We formalize this by introducing the definition of diversity order D. For a code C, it is defined as the log of probability of error to the log of epsilon as epsilon tends to 0. So, for the non-ergodic channel, you see with a repetition code it is going to be L. For a non-trivial code it is going to be capital N. If remember from geometry, this term is essentially going to be the slope of the probability error curve. Okay, so D is the slope of the probability of error curve. Yes, any questions here? So now we have formally linked diversity order, okay, and degrees of freedom. Remember that. And recollect, diversity order in an IID binary erasure channel is upper bounded by D min, right? The minimum Hamming distance of the code that you are using, and that is upper bounded by N, because there cannot be more than N number of, there are N number of terms that are required to completely characterize the channel. So the diversity order cannot be greater than N. Similarly, the diversity order of a non-ergodic BSC is upper bounded by L, and L is again upper bounded by N, and it goes without saying that D min is greater than N. So in fact, I could have made this bound tighter by saying L is less than equal to D min is less than or equal to N. Okay. So as such, non-ergodic channels are also called as limited diversity channels. So the diversity that they offer is going to be limited. So the number of independent replicas that you are going to get, on an ergodic channel is going to be much more than the number of replicas that you are going to get in a non-ergodic channel. So remember that this is an important classification. Non-ergodic channels are basically limited diversity channels. Okay. Now, how does this help me in designing a code for an array channel? The code design criteria for for an ergodic channel would be very simple, but the criteria for a non-ergodic channel would be a slightly different. You see that? Suppose WL is the Hamming weight of the block CL. The code word WC is the sum of partial weights. The code word weight WC is the sum of partial weights. So there is a missing term here. This is basically omega L. Okay. So the code word weight is going to be the sum of partial weights. Now you can simply imagine that if C is a full diversity code, if under ML decoding non-ergodic DC all partial Hamming weights are non-zero. Okay, that means in link properly, so you get exactly what you receive, or in the second case you don't receive anything at all. That is an erasure channel. So the first block basically models your erasure channel. In contrast to fading channel, instead of code word you transmit a symbol from a constellation, here a QCOM. The symbol is multiplied by a code by an attenuation alpha. That after that it is added by a white noise, and that's what you receive. Okay, so you can visualize the two channels entirely differently. The diversity order of fading channels. Remember that diversity order is the slope of the probability of error curve. Higher the slope, the better the channel, because with small increase in or a small decrease in epsilon for the erasure channel will result in a large decrease in probability of error, right? Epsilon power L or epsilon power n or epsilon power d mean, remember that. Okay, visualize that. So diversity order is very important in erasure channel. Now we link that to fading channel, because we now have a link from the previous definition between a fading channel and an erasure channel. So definition of diversity on PEC and code design criteria can be directly lifted from erasure channel to fading channel. The only difference you need to make is replace epsilon, the erasure probability, by the signal to noise ratio. That is the signal to noise power, E of xi square by E of eta I square. That is the signal to noise ratio. Average received power, average transmit signal power by average noise power. Okay, that gives you the signal to noise ratio. So that is one thing. The probability of error of a fading channel now is proportional to epsilon power L in an erasure channel, and it becomes 1 by gamma power L in a fading channel. Okay, see the relation between the probability of error for an erasure channel, non-ergodic erasure channel with L degrees of freedom or diversity order to that of the probability of error of that also remember that this is the average signal to noise ratio. Okay, and remember that the coefficient alpha we have already assumed HI, the entries of the channel matrix is has variance 1, so that will average out. Okay, so this is actually the mean signal to noise ratio, or the signal to noise ratio if it was a seesaw channel without any fading. Okay, now we can define the diversity order of a fading channel. You see that D is the diversity order is limit gamma tends to 0 log of P by log of gamma. See the difference from the previous case, you have a minus sign, as compared to the erasure channel you have a minus sign here, and instead of epsilon erasure channel, you have the signal to noise ratio term gamma here. So this gives you the diversity order. See now, I hope you now see the benefit of my introduction of the erasure channel. I did not have to go through the entire derivation of the probability of error. It can be done. It is there in many of the textbooks. Okay. But here, I have been able to lift the concept from the binary erasure directly to the fading channel with some small changes. Okay. Now, I would like to come up with design criteria for fading channel. So now, remember from the block diagram for erasure channel and fading channel, in the erasure channel the code word is directly transmitted. In the fading channel the code word is modulated, and the modulated signal is transmitted over the channel, it is attenuated, and then noise is added. So now assume there are two code words C and C dash, and there are two modulated symbols X and X dash. Okay. Remember that C and C dash are both vectors of length n. Now what we do is, as in the erasure non-ergodic case for the erasure channel blocks, so we have NL components in each block, and let WL be the weight of the L block in the difference X minus X hat. Okay. See that X and X hat are now points from a constellation. Okay, and these points are points in a for example in a two-dimensional space if you are taking quant. Okay, take an example. Suppose n is equal to 4, you are taking 4 quam, or you are taking 4 am. So it takes 4 values, minus 3, 1, minus 1 and plus 3, plus or minus 3, plus or minus 1. These are the 4 values, that is, I am assuming a 4 amplitude modulation. Okay, the block length of the code is 4, and block length of the code is 4, and there are 2 blocks, so L is equal to 2. So what you see, you have an X, plus 1, plus 1, minus 3, minus 3. So first 2 bits correspond to first block, second 2 bits correspond to second block. Take X hat. So yeah, I am taking example minus 1 in the first block, minus 3 in the second block. Now subtract X and X hat. So what do you see? So first 2 terms will differ, but second terms will cancel out. So what you have, the weight, remember the weight of number of non-zero components in the difference. So you see the number of non-zero components in the first block is 2, in the second block is 1. Take another example. Take X hat is equal to minus 1, plus 3, plus 3. So here you see that the weight WL or W1 is 1, because in the first block they differ in one place, but in the second block they differ in both the places, so W2 is 2. Now with these 2 correlations, remember that first correlation, instead of epsilon we have 1 by gamma. Okay, and the second, instead of the Hamming weight, we have the weight of the difference of the 2 symbols. Okay, or 2 symbol vectors. With these 2 different variations, we now have the design criteria for a non-ergodic fading channel. Suppose C is the full diversity ML decoding on a non-ergodic fading channel if and only if all partial Hamming weights are non-zero. Same argument that I explained while doing the ergodic channel case. Okay. So the code design criteria for a non-ergodic fading channel, okay, is that the difference of 2 symbols corresponding to 2 different code words are such that their partial weights are non-zero over all blocks. then you get the maximum diversity that is possible on a non-ergodic channel, that is capital N. Okay? Till now we were discussing the CISO channel. Now we will go to the MIMO channel. In the MIMO channel, the probability of error or general probability of error. I am not telling you how it is derived, but what I am telling you is can be represented as 1 by G gamma. Gamma is the signal to noise ratio over a single channel. Okay, average signal to noise ratio over a single channel, or the signal to noise ratio over a AWGN channel. Okay, and D power D. This is the general form where the probability of error of a MIMO channel can be written as. The D is called as the diversity gain and G is called as the coding gain. This can be seen by, I'll show you a plot. I'll basically make a plot to show you how things are. Okay, so this is a the x-axis is basically your gamma. So the x-axis is basically gamma, the signal to noise ratio. So on this axis the signal to noise ratio increases. I'll put it in dB. Okay. The y-axis is probability of error. Typically it would be log of probability of error. I'm just writing in or semi-log scale. So let me plot that. You have already seen the gamma curve. So this is 1 by gamma. This is 1 by gamma square. Okay. Yeah, something of this kind. Okay, so this is 1 by gamma power 4. You see that as the diversity order D is increasing, you see that the curve is probability of error has a sharper slope, and what you see is, suppose this is some probability of error. Let me put, I am just giving you an example. Let this be 0.01. Okay, so to get the same probability of error, if you have a diversity of 4, you need a much smaller signal to noise ratio as compared to gamma square, and that compared to 1 by gamma. So the diversity order is very important in fading channels. The larger the diversity order, the very more better your quality of curve is. So you see that in the original second slide that I showed you, remember that I said there is a 40 dB requirement to get 10 power minus 6 probability of error on a CISO fading channel. But you replace it now by a channel with 2 degrees of diversity, gamma square. In this case, the probability of error that you will get equal to 10 power minus 6 will occur at around 27 to 28 dB. So that is a reduction in requirement of almost 22 to 23 dB as compared to CISO channel. Okay, it comes around 5 to 6 dB. So it is almost as near. It is 16 dB for getting a probability of error of 10 power minus 6. Okay, so you see that the important point is diversity is what I had told you at the start is a way of taking care of, diversity is a way of taking care of fluctuations caused due to fading. The main culprit for degradation of performance over a wireless channel. Okay, and diversity is a low power solution to combating that problem. So you see D, I have explained how D basically affects the channel. Now I will explain how G affects the channel. So I will take the case of the gamma square, so I am rubbing off the rest of them. Yeah, so this is your 1 by gamma square curve. Now suppose you have a G. Assume that this is, here G is equal to 1. Now, if you have G equal to 2, what you will see is a parallel curve. This is 1 by gamma square curve. The second one, 1 by 2 gamma square. Okay. So, what you see, the coding gain will not change the slope of the probability of error curve, but it will result in shifting of the curve towards the left hand side. So it will still require smaller power, but it will not give you the large diversity gain. So diversity gain, remember that at smaller SNRs you have small gain, but as the SNR increases, the gain also increases. So that's a very important differentiating point as compared from coding gain to diversity gain. Okay. Now, remember the MIMO channel that was defined on the previous channel. It has how many degrees of freedom? Very simple. You are transmitting NT symbols from the transmitter, but you will need to know all the NT-NR channel coefficients to completely know the signal at the receiver, right? So that's why the degrees of freedom of the MIMO fading channel is going to be NT, NR. But depending on the code we use, this diversity or the degrees of freedom can vary between NR and the maximum NT, NR. Now tell me why NR is a lower. That is because if you are going to replicate, for example, what you transmit on all the channels, then you will have a single there will be no diversity across the transmit antennas, but there will be diversity across the receive antenna. So that's why you will have NR different replicas at the receiver. So that is going to be the minimum. Okay. So your code that you use over MIMO, the maximum diversity order it can have is NT, NR, and the minimum it can have is NR. So yeah. For a MIMO channel, this is an important point to remember. The diversity order will be between NR and NT, NR. The addition, there is a second term that I am introducing here, the ratio D by NR. This gives us the transmit diversity. This is the it is the effort that the transmitter is making to contribute to the diversity. Receiver diversity, because there are different channels at the receiver, that diversity is ensured. Okay. So D by NR is basically the transmit diversity term. Okay. So these definitions are clear. Also, recollect from the MIMO channel model, y is equal to h x plus eta. Okay. From there you can make another conclusion. The space dimension for one channel is NR. That is, you channel only on one transmit antenna, so you get a receive vector that corresponds, or a column vector which has NR different terms. Suppose you are transmitting on second antenna, okay, so you will get the second column of the H matrix, okay. So this has a dimension space of NR, okay. So at the receiver, the signal that you receive is going to be Y1, Y2, Y3, YNR. So the receive vector Y has only NR degrees of freedom. So while the channel has NT, NR degrees of freedom, what you receive is going to be only NR. So in order to receive or in order to get the full diversity possible on a channel, what you need is NT channel uses. So that's why the concept of space-time coding comes into picture. Okay. See remember the vector. If you want, I will write it down here on the whiteboard. Yeah. So remember the channel model. I is equal to H X plus eta. Okay. Your H is an NT cross NR matrix. No, NR cross NT matrix. Okay. NT transmit vectors, NR receive vector. Your Y is a NR cross 1 vector. So while total number of independent variables here are NT cross NR in the H channel, number of independent variables in at the receive vector is NR, so you cannot get full diversity. So this idea, okay, this idea basically leads to the concept of space-time codes. Okay, you know it is not just sufficient to transmit it in space across the anti-transmit antennas. You also have to transmit across time. You have to replicate or add redundancy through a code in both space and time. So that gives you the concept of space-time codes. Now, the main objective of space-time coding is to build easily decodable codes that maximize both the coding gain and diversity gain for a given information rate. Yeah, while they are setting it up, we can discuss one of the questions that has been taken here. See, in the narrowband model that I have introduced, GCT, I am addressing your question here. In the narrowband model that we have assumed here, the extension that I have given, you see that if you put distance between the line of sight and yeah, so now the main objective of space-time code is to maximize both the coding gain and diversity gain for a given information rate and also to make the code easily decodable. So let RC is equal to the ratio of the information symbols to the code symbols. Then the information rate in bits per channel used for a space-time code is defined as NT times RC into log Q. Okay, where Q is basically we are assuming Q array alphabet, that is QQM or QAM or whatever it is. Okay. Distributing the components of a space-time code and NT transmit antennas is referred to as the spatial multiplexing. Okay, and when compared to the CISO channel, remember that the MIMO has additional two terms. That is basically NTRC. And this term is basically what is called as the multiplexing gain. From an information theoretic perspective, this is formally defined as the ratio of rate of the code, space-time code, to the log of SNR, okay, as SNR tends to infinity. So this basically tells us the number of independent streams that we are going to transmit on the MIMO. Okay, so there are two terms of the code that are unique. One is the multiplexing gain, and the previous one we have seen is the diversity gain and the coding gain. Remember, we have linked diversity gain to degrees of freedom. Okay, that's an important concept. The diversity gain has been linked to, you can also view it like this. Suppose you are doing no coding, then at each NT channel you can transmit an independent symbol, right? So you can at max have NT number of different streams, but there is no guarantee what, there is a guarantee on the diversity gain, it will have at least NR, but it may not have full diversity gain. So that is basically a trade-off in the design of space-time code that we will take care in the third lecture. Okay. So with that, I will summarize today's lecture. What we have done is we have today introduced the various impairments in the fading channel and contrasted that with the AWGN channel, and we said that the fading is the main problem. Solution to that is basically diversity. There are many ways of diversity and then a very important approach of getting diversity is space or antenna diversity, where you get uncorrelated replicas by separating antennas in space. Okay. Then we modeled basically the number of then we tried to get a general model of the MIMO channel, and then we showed that simple model of flat slow fading channel. Okay, that a channel that is invariant to change in time for the duration of interest, one, and second, all components, frequency component of the symbol or transmit signal go across the same fade. If you have a frequency selective channel, it can be easily taken care by going to MIMO, because from a MIMO perspective, the frequency selective channel becomes a flat fading channel. So that's why this model is sufficient. Time varying nature, I have told you, because in most practical cases during the duration of interest, for multiple transmit symbols the channel is going to be constant, so it is basically useful to assume, or it is practical to assume that the channel is constant. Okay, so then using the example of a erasure channel, because probability of error expressions etc. are very easily derived for an erasure channel, I have basically introduced concept of degree of freedom, linked it to the diversity and then applied it. I have introduced the concept of ergodic and non-ergodic, and then I have applied it to a fading channel. Okay, yeah, and then I have introduced by writing a general expression for a probability of error for a channel, I have introduced a space-time code from the perspective of trying to achieve full diversity. And I have shown you that you cannot have full degrees of freedom because the received symbol has only NR variables. So it cannot have a NT-NR number of degrees of freedom that is there in the channel. So you need to do something in time. Okay, you definitely have to have NT replicas. Then only you are going to get a diversity of order of NT-NR. Okay, so that summarizes the complete discussion till now. So now going to questions, there is one question from GCT. Yeah, first GCT, you have asked relationship between angle of arrival and line of sight. See, line of sight would be a straight line. So angle of arrival will be relative to the line of sight. Okay, it is the angle of arrival of a multipath other than the line of sight will basically give you the angle of arrival. See, if you have a line of sight component, then that's where you get the Ricean channel, and if you don't have a line of sight component, that's where you get the Rayleigh channel. I am replying to your question. Array gain, you can take it as coding gain. Signal processing guys will typically call that as array gain. It is characterized in another way also. It is the average. If you take a code and you take a ratio between signal to noise ratio, basically then the additional factor you get by using a space-time code is what is known as the array gain. Okay, but from a coding perspective, I would say that the array gain is same as the coding gain. Yeah, TC, you have asked. Yeah, TC, you have asked what will be happen if we do not have narrowband assumption. So, yes, sir. If you don't have narrowband assumption, basically you will have a multi-tap channel. Okay, so what you transmit will be received at different durations that will be seen as different replicas at the receiver. Okay, so it will result in a multi-tap channel. A multi-tap channel can be converted to a flat fading channel by basically using OFDM principles. So frequency selective channel becomes a flat fading channel when we apply MIMO. Okay, so that's why most of the cases you will assume flat fading channel. Does that answer your question?
Yes, sir. Thank you, sir. Thank you.
Reply to your question. Yes, case RCT I have already replied to your question. From a probability of error perspective, coding gain and processing gain are same. Okay, from a signal processing or a antennas perspective, if you combine signal from multiple receive antennas, what you get is called as the processing gain. But from a coding perspective, from a probability of error perspective, what the processing gain will result to is essentially coding gain. So for me, coding gain is same as processing gain or antenna gain. Okay? Yes, PSGCT, you have any questions? See, the relation between signal to noise ratio and bit to noise ratio is very straightforward. Right? If you are using BPSK, it is going to be same. If you are using QPSK, then it depends on how you are mapping the bits. Right? So that's going to be a very straightforward relation. It is going to be the number of bits multiplied by the EB by N naught, that will give you the signal to noise ratio. Okay? Does that answer your question? Okay, there are no further questions. You can close the session now. But important things that you should remember is how I have introduced the concept of degrees of freedom. Based on the degrees of freedom, how I have introduced the interlinked it to the probability of error for a MIMO channel. And then how I have justified that it results that you require space-time coding. Okay?